Hi, how's it going? This video maybe looks a little bit different than some of the others. That's because it's recorded about a year later. I've lost some weight and I'm wearing a t-shirt from Epoch, which is a Canadian technical death metal band of my acquaintance. If you're into technical death metal, which is probably vanishingly improbable, I think, for this audience, but I might be surprised, maybe you should check out Epoch. The first letter is diphthong A and E. Anyway, sorry, that's off topic, but I've kind of gone for the not so fancy and professional looking t-shirt just for today, just for something a little bit more casual. So basically this is a reshoot of a video. Melissa was watching very closely indeed, props to her for that. She noticed that the PowerPoint in the PDF was 3 slides longer than the video. For some reason, either I chopped the video off short when I uploaded it, or I just stopped talking before the last slide in the video. So there are more slides, so I'm going to basically reshoot from scratch this particular discussion of quantum and basically replace the video that was there that was cut short. So that's the quick version. Interestingly, I've also discovered in the meantime that, sorry, I've got to figure out which way to move. Some of what I said in the first video was erroneous, historically speaking. So it's probably good to have an opportunity to fix that as well. So the ultraviolet catastrophe is a thing. The Rayleigh-Jeans law basically relates temperature of a body to the amount of energy released by it. And it's basically that the amount of energy released, the power is 10 to the 4 times the temperature. And as the temperature goes up, the power goes up. But the Rayleigh-Jeans law basically in the ultraviolet end, which is the shorter wavelength, higher energy end of the spectrum, if you keep increasing the temperature, the energy produced goes to infinity, which is clearly not possible physically. Infinite energy is more than all the energy in the universe, so it doesn't really work. So what was broken was not the universe, but the Rayleigh-Jeans law. So a number of different solutions were tried to solve that, and it turned out that quantum did solve it. But the way the story is usually told is that Planck was trying to solve the ultraviolet catastrophe and discovered quantum in the process of trying to solve that. And in fact, that's not the case. Planck was not concerned about the ultraviolet catastrophe. He discovered quantum in a different context, but it does actually solve that problem. If the energy of photons is quantized, in other words, if it's in small finite packets rather than continuous, then that solves that problem, and the solution of the Rayleigh-Jeans law, or the modification of it, actually predicts exactly what does happen as you heat something. So, as I say, that's a historical correction from what I said last time in terms of the causal connection between these processes. Planck wasn't actually trying to solve the ultraviolet catastrophe. We talked about relativity and some of the little bits and bobs and ends of things that were still to be solved. Remember that at the end of the 19th century, physicists pretty much thought that we had the universe under control. We had Newton's laws, we had a pretty good understanding of most things, but there were just a few phenomena that were strange and odd and not easily explained using our current science. And one of those was the photoelectric effect. So Einstein, among others, developed an explanation of the photoelectric effect and the reason that it actually worked. Now, sorry, I'm trying to think what's on the coming slides because I don't want to preempt myself. So remember that Newton and Huygens had argued about whether light was a wave or a particle. Newton had thought that light was a corpuscle, thought it was a small particle. Huygens suggested that it was a wave. And Young's double slit experiment, which involves interference, which is a wave phenomenon, supported the idea that it was a wave. So really from that controversy in the 17th century on through, the notion that light was a wave had been the prevailing concept. But a wave is continuous. A wave has continuous energy. If you have an ocean wave bringing energy to the shore, it just keeps on coming and coming and can build up over time. A particle is discrete. It brings a packet of energy, and then that particular packet of energy has a particular size. It's quantized. It's a quantum. Quantum just means a specific quantity. So the photoelectric effect is that if you shine light on the surface of some metals, electrons will be ejected. So the electrons will pop out of the surface of the metal, and they will pop out with some energy, some kinetic energy, and fly away. There are ways to measure those electrons as an electric current over time. And it turns out the photoelectric effect has this feature. If you use light of too low a frequency, too long a wavelength, too low an energy, then you can make it as bright as you want and shine it on the material for as long as you want, and no photoelectrons will be ejected. Photoelectrons are just normal electrons, but they're ejected by light. No matter how intense, no matter how much of the low energy light you put onto something, you will not get a photoelectron. On the other hand, if you go to a shorter wavelength, higher frequency, higher energy light, and shine that on the material, even a few photons, even a very small amount, very dim, very quick, will start ejecting photoelectrons. So a wave phenomenon doesn't explain this well. A wave phenomenon would be, the waves would be coming in, they'd be bringing energy, and you would just allow it to accumulate over time, and eventually the electron would have enough energy to escape. So a wave phenomenon doesn't explain the photoelectric effect. A particle explanation does. So if a particle of energy comes in and has too little energy, then it can't allow the photoelectron to escape. It doesn't have enough energy to allow the photoelectron to escape. So you can send 1 million of them, but if they, well, it'll be multiple trillions of them, but if they don't have enough energy, the photoelectrons won't escape. Whereas even just a few high energy photons, high energy quanta of light energy, will be enough to give the electrons the energy they need to escape from the material. We talk about the work function for a particular metal. That amount of energy that's required to escape is different. So for cadmium versus aluminium versus iron and so on, the various photoelectric metals, the amount of energy required to release the photoelectrons differs, and that's called the work function. There's a lot of detail in this experiment, and textbooks will talk you through it and give you good diagrams, or there are various videos on YouTube that will explain the photoelectric effect really clearly. But the key point was that a wave explanation had been rejected, and then it was kind of brought back. Sorry, a wave explanation had been accepted, a particle explanation had been rejected, but it was brought back by the photoelectric effect, because waves don't explain it, particles do explain it. So the notion of a quantum, Einstein suggested that light energy is in these little packets, and we call them photons. Photon is just the name given to a little quantum of light energy. And that these quanta have a specific energy based on their frequency. So this equation E equals hf, the energy in the photon is Planck's constant, which is very tiny, by 10 to the minus 34 meters squared per kilogram per second. So it's a very tiny amount of energy, but multiplied by the frequency in 10 to the minus 1, gives an energy in joules. So if you work out those units end up being joules if you multiply meters squared kilogram per second by per second, because a frequency is a hertz, it's a per second. So you end up getting meters squared kilograms per second squared, which is a joule. So a particular photon at a particular frequency has a particular energy. And this was part of the insight that Einstein had in about 1905. Between 1905 and 1915, he did all this good stuff. This might have been I'm not 100% sure which of those years it was, two miraculous years that he had publishing really interesting work. And then getting the Nobel Prize another 15 or more years later than that, maybe 20 years later. We could talk about the Nobel Prize and the politics of same and why it takes a long time for really groundbreaking discoveries to be recognized in that way, but that's a whole other conversation. So, all right, I did preempt what was coming in terms of the slides. This is one of the problems, as I may have mentioned before, when you know the topic quite well, the order you present it in sometimes changes up. So Newton talked about particles, Huygens talked about waves. Quite a lot of the behaviors of particles and waves are similar, so it can be explained by both. So reflection, if you shine a water wave hits the beach at an angle, it's reflected back at an angle. Angle of incidence equals angle of reflection. So it's explained by a wave, but if you throw a tennis ball at the ground, it bounces off at angle of incidence equals angle of reflection as well. So both waves and particles explain reflection. Refraction actually, waves in more dense media slow down. Particles notionally in more dense media would have speeded up. If Newton had been correct and there were corpuscles, the speed of light in a more dense, more optically dense medium would have been faster rather than slower. It turns out that it's slower, and we found that out later. But at the time, there wasn't a way to tell. But the double slit experiment, the fact that if you shine light through two slits, it needs to be monochromatic light. So you need a laser or some other source of just one color. Just a filter that keeps it the same color will work. Then the light from each of the two slits goes to a screen. Where there's constructive interference and the waves overlap positively, it gets brighter. Where there's destructive interference and it cancels each other out, it gets darker, so you get a pattern of bright and dark fringes. Now that doesn't happen with particles. If you're throwing tennis balls at two slits in a wall and then looking at the marks on another wall at the back, you expect two bright patches, and that's all. That's what we'd expect with particles, but what we see is wave behavior. So, as I say, that was considered definitive. Oh, light is a wave. But it turns out that no, what you actually get with the photoelectric effect is something that's best explained by a particle. We talk about wave-particle duality of light, but I would argue it's actually better to think of light not as light as a wave, not as light as a particle, not as light is both a wave and a particle. It's better to think about it as light is light. Light is an electromagnetic effect where a electric field wave produces a magnetic field wave and vice versa, but it's also quantized into small pieces that arrive at the same time. So light is light. Light is its own thing, but we use light, particle behavior and wave behavior as metaphors to help us understand. So light behaves sometimes like a particle and sometimes like a wave. Doesn't mean it is a particle or a wave, it means it's behaving like a particle or a wave. Or we're using particle or wave behavior as a metaphor to understand light, but light's just being light. Light's just doing its thing. So I think that's probably a helpful way to think about it. So once you got the idea of quantum, Bohr and Planck and others who were working at the time were able to, Schrödinger and Heisenberg and all of these kind of names from that particular era were able to explain quite a lot of other phenomena. Once you get the quantum notion, then you move on to things like the structure of matter as well. So we had the notion of atoms as indivisible, undividable, uncuttable, which is what the word atomos actually means in Greek, not able to be cut, which came from Democritus, who originally came up with the idea of atoms. John Dalton returned us to it quite a lot later. And I realize I'm kind of digressing into chemistry a little bit here. But then we had Sir J.J. Thomson discovers the electron and realizes that the atom can actually be divided, that there are subatomic particles. The electron, which has a negative charge. J.J. Thomson talks about the plum pudding model, which is a large positively charged pudding with electrons as these negatively charged plums through it. And then Rutherford does his famous alpha particle scattering experiment and sends alpha particles at the atom, and they bounce back or are massively deflected. He says, I was as surprised as though I had fired a cannonball at tissue paper and it had bounced back and hit me. It's a nice turn of phrase. And so we end up with the Rutherford atom, which is a positive nucleus and some kind of negatively charged cloud around it. And then when you get beyond that, you start saying, well, why do we actually see emission spectra? Why? Hydrogen is quite simple, other elements are quite complex. Hydrogen, just because it has one proton in the nucleus and one electron surrounding it. So what happens when that electron gains energy or loses energy is fairly simple. As soon as you have even helium with two protons and two electrons, then they're all starting to interfere with each other and it gets very complex very quickly. But the hydrogen spectrum, Lyman, Balmer, Paschen and Brackett series of lines within the hydrogen spectrum are explained by a quantum model where the orbitals are quantized. So it's not an orbital model like a solar system where things can orbit at any distance. Rather, there are particular specific orbitals. There are the s orbitals, the p orbitals, the d orbitals, the f orbitals. Again, we're getting a bit chemical, but basically the thing is, like the photoelectric effect, if you've got an electron in one orbital and a photon of light comes in and has enough energy, it will lift the electron to a higher energy orbital. The electron will orbit there for a while, but it's not stable, and it will drop back to the lower energy orbital and release a photon of light, release the energy that it gained as a photon of light. Now, that behavior explains the spectrum, the emission spectra, in a way that just a planetary orbit model doesn't. So again, the quantum explanation opened up new explanations. Sorry, it opened up new ways of understanding the behavior of matter at the tiny scale. Remember I mentioned before that relativity happens at the large and the fast scale. So we need to take general relativity into account when we're talking about stars and planets and solar systems and galaxies. We need to take quantum into account only at the very tiny scale. At the scale of photons, it's very important. At the scale of electrons, but by the time you get up to the scale of an atom even, which is obviously still extremely tiny, it's starting to behave more like the classical world that we live in. Now, both of these things are quite mind-bending for us because we don't live at the galactic scale, or relativity would be relevant to us, and we don't live at the atomic scale, or quantum would be relevant to us. We live at the classical scale in the middle, so our world behaves in quite predictable ways, but at the quantum scale, things are much less predictable, much more probabilistic, and not chance, but so for example, for most quantum things, most quantum mechanical things, we can work out the probability of the electron being in a place. We can't say precisely where the electron is, but we can work out there's a probability of X% that it's within this region here. So we can talk about that a little bit. One of the ways that the notion of orbitals around the nucleus was developed was thinking about the electron's movement as though it had a wave nature. That even though, so we started off with light, photons, having a wave and a particle nature, and kind of extended that notion to other kinds of matter, that electrons also have a wave and a particle nature. That we tend to think of electrons as these hard little ball bearings, but they behave more like they have a wave nature as well. So if you imagine waves going around the nucleus in an orbit, if you have a whole number of waves, you can get an orbit. If you have a non-whole number, 7.5 waves, then they're not going to connect up at the end. So you're not going to be able to get an orbit. So that's one way of thinking about the orbitals. Now, remember that actually the orbitals aren't all spherical. The s orbitals are spherical in shape. And again, that's not a circle, that's a sphere. And then the p orbitals have these kind of petal infinity symbol shapes in 3 dimensions. The d orbitals have a petal shape with a donut around the middle and some flower shapes and a whole variety of other things. So the orbitals are not spheres or circles. They are these probability regions in space. But nonetheless, the notion of a wave nature of matter was quite important in the development of these ideas. So Louis de Broglie, Count Louis de Broglie, I think, talked about this idea that particles, electrons, have a wave nature. So this equation, which we could rearrange to make lambda the subject, so the wavelength. So you can calculate the de Broglie wavelength of anything. P is the momentum, P equals mv, so mass times velocity. H is Planck's constant, which remember is very tiny. And because it's very tiny, the wave nature of things like us, or an elephant, or a Boeing 747 is imperceptibly tiny. So we do have a wave nature as well. A Boeing 747 has a wave nature. If you calculate its mass, which is very large, its velocity, which is very large also, 1,000 kilometers an hour or so, you can calculate what its de Broglie wavelength is, but it's still on the order of 10 to the minus 30, I think, from memory. So 10 to the minus 30 meters is nothing we're going to notice in everyday life. So this wave nature, this is one of the reasons that the quantum world is the world of the very tiny. It's when you have very, 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 very tiny masses, the mass of an electron 10 to the minus 31 kilograms. So when you have very tiny masses, this stuff becomes relevant. The de Broglie wavelength becomes relevant compared to the size of the particle and the area it's moving in. So it's one of the reasons, as I say, that the quantum is the world of the very small. So the uncertainty principle has been used and abused in popular culture quite a bit. So let's talk a little bit first about what it is, and then we'll talk a little bit about what it isn't. So if you have a look at the equation first, let's start with the equation. Delta P, delta X is greater than or equal to h bar on 2. Delta P is the uncertainty in the momentum of a particle. So usually the mass doesn't change, so it's the velocity that's changing. And delta X is the uncertainty in the position. So what the uncertainty principle is saying is that we can't know the uncertainty in the position times the uncertainty in the momentum has to be greater than or equal to this number h bar on 2. H bar is just Planck's constant, h, which is that 6 point something by 10 to the minus 34, divided by 2 pi, and then that again divided by 2. So we could write it as h over 4 pi if we wanted to, I guess. So that's a very, very tiny number. That's something by 10 to the minus 34 divided by another 4 pi, which is about 14 or something. So it's a very, very tiny number, which means that the uncertainty is not great. The uncertainty is relevant for things on the scale of electrons, but the uncertainty for everyday stuff is not great. So when you hear people say, oh, the uncertainty principle means we can't know anything, everything's open, and my homeopathic explanation is just as good as your scientific explanation because uncertainty principle, no. That's not what the uncertainty principle says. The uncertainty principle is very specific, it's physical, it's measurable, and it's very, very tiny. But it's important to know about. So as I said, one of the things about the quantum world is that it's quite unintuitive, quite weird, quite strange. The notion that we simply cannot know something, and it's not about our instruments, it's not about our ability to measure, it's a feature of the universe, that we can't know something to an arbitrary level of certainty. We are limited by the limitations of the universe itself and its behavior. Is, as I say, it's quite unintuitive, it's quite challenging to us because we're used to being able to measure things very precisely. But it is nonetheless the way the universe is. We've measured it, we've tried it, and this is what it is. There's some really interesting work around weak measurements. If you actually Google my name and weak measurements, you will find a paper that I wrote a few years ago about it. It was basically a student assignment when I was working at UQ that I turned into a paper on a non-peer-reviewed site. But it's kind of fun, I don't know, if you're really, really interested in it. Promise it won't be on the quiz though. All right, and then one last thing, I guess, the Stern-Gerlach experiment was one of the things that tested the quantum model and was quite important. So this is a probably oversimplified version of it, but it gives you the key points, which is that Young's double slit experiment back in the 17th century showed that light behaved like a wave. In other words, you got this interference pattern, the bright and dark fringes, showing that light had a wave nature. The Stern-Gerlach experiment did the same thing with electrons. Fire electrons at two slits. Now, if you think about electrons as these small steel ball bearings, these particles, then you'd expect two bright stripes. But in fact, what you get is an interference pattern, a pattern of bands. So electrons have a wave nature. This experiment demonstrates that electrons have a wave nature. But the really interesting bit about it is that if you then put a sensor on one of the slits so that you know which slit it went through, then what actually happens is that you've conducted an observation of the nature of what's happening with the electron, and that observation is telling you some information, and that actually changes the way the universe behaves. So if you're firing single photons one at a time at the double slits, you'll still get an interference pattern unless you put the sensor on one of the slits and know which one the electron went through. If you know that, if you measure that, then you'll get a single spot or a single line on the screen. The electron will switch from behaving like a wave, where it's got this wave nature, it's spreading out, diffracting through the slits and interfering with itself, and it will switch to having a particle nature and hitting one spot on the screen. Now, this is some of the weirdness of quantum, that the things that we measure change what happens in the universe. If you turn the sensor off, then you get wave behavior. If you turn the sensor on, you get particle behavior. So it is strange, it is brain bending, but it is observed, it's measured, and has been since at least the 60s. So we've got 50 years of experiments backing up the fact that, weird as it is, this is how the universe is. Occasionally you'll hear discussions from quantum deniers who want to come up with another version or another understanding of what the universe is like that doesn't use quantum, but they tend to never hold up if the experiments are actually done. It seems that this is the way the universe is. Now, we might develop a big grand unified theory at some point that unites relativity and quantum, because that would be really cool, because we've got a discontinuity. We've got what happens at the big, what happens at the little, and the two don't actually work together. The two theories don't seem to be consistent with one another. What we want is a grand unified theory that combines both of them and explains all of those behavior, but we haven't got it yet. Maybe we need the next Einstein to come along and develop that. I kind of hope that the next Einstein is a young lady from the developing world somewhere, because there were far too many old white dudes like me in that list of names that I gave towards the start of quantum. And I think it's going to be really fascinating to see where physics goes over the next few decades. I think there's lots still to be discovered, and that person might be someone in one of your classes. You may teach the next Einstein, which is kind of a humbling and amazing thought. So hopefully that's given you a sense of quantum. Certainly read more, watch more, get more of a sense. It's been a very quick run through of what's a very complex topic, but hopefully interesting and useful to you in your teaching. Thanks a lot. See ya.